talked about zero-range processes in this conference. I'll say a few things about it. I'll use the conventions followed in Landim's book, in the Kipnis-Landim book, where I will consider my particles to live on the discrete torus with periodic boundary conditions. And the state space will be the space of all configurations of particles. So will be functions that are defined, take integer values and are defined on this torus. So the points of the state space will be such functions, where eta of x will be the number of particles at site x. And the stochastic dynamics of a zero-range process to be defined on this state space depend on two parameters, a local jump rate function, which describes the rates with which particles jump, and the transition probability on the integers, which describes how particles that jump move when they jump. We will assume some conditions from the jump rate function. Yes? Yes? Okay. Okay. We will assume some conditions, technical conditions from the jump rate. The first one is a node degeneracy, that the only way that you will have zero rate of jumps is when you don't have any particles. The other condition is a Lipschitz condition. This is mostly important when you want to define the zero-range process dynamics in the full lattice, but it also plays some roles when you try to obtain hydrodynamic limit. And finally, there is one third condition, that this lim-inf is strictly positive, and this is required to guarantee that you will have equilibrium states that correspond to non-zero densities. Otherwise, you will get only the trivial equilibrium state that corresponds to the zero density. And we will assume for the step distribution P some conditions also, which will be to be spatially homogeneous, have a mean zero, and correspond to an irreducible random walk kernel. One can define such a distribution by kernel by choosing a distribution on the integers that has mean zero, to support span ZD, and defining the probability to go from x to y as a probability of x minus y. This defines by stochastic probability, which also has a correlation matrix with strictly positive definite, the covariance matrix. And having these two ingredients, these two parameters, one can define the zero-range process as the Markov-Chain process on the state space of the configurations with generator given by this formula. This means that a particle makes the transition from x to y with a rate g of eta x, the rate to leave a site that has eta of x particles, and with this probability to make this transition. Here, this is standard. This means the configurations that results by moving a particle from x to y. This is a zero-range process. And one can describe heuristically the dynamics this way. If you start from an initial configuration, eta 0, you wait an exponential time of parameter which is equal to the sum of all the jump rates at the sites, at all the sites. And then when a exponential clock of this parameter rings, you shift to a new state, and you choose your new state with probability proportional to the jump. This is the proportion that the probability that you will have a jump at the site x, and this is the probability that you will move from x to y. And when this jump is made, the clocks are reset, and everything starts again with the new state being the new state that you achieve. Okay, the conserved quantity is the total number of particles, and this is one that we want to describe in hydrodynamic limit. The dynamics differ depending on whether the jump rate is increasing or decreasing. For instance, when you have increasing local jump rate, particles jump with higher rates from sites that have a lot of particles. And the simplest example is when you have the identity function, which corresponds to having a system of independent random walks. While in the case that we are mostly interested is when you have a decreasing local jump rate, in which case particles tend to jump with lower rates from sites that are occupied with high numbers of particles. And this sticky behavior is what leads to the emergence of condensates, possibly. Particular example that has this behavior of exhibiting condensing and phase transition is the Evans model, where the jump rate is defined by this formula. This is the simplest case. Usually they have a gamma between 0 and 1 here, but I'm only considering this case for simplicity. And to describe the hydrodynamic limit now, one needs to first describe the ground canonical ensemble, which will give a way to describe hydrodynamic limit via the principle of conservation of local equilibrium. Ground canonical ensemble for a zero-range process is the family of its product translation invariant equilibrium states. To obtain it, one has to solve this equation with the generator, and assuming that you have a solution that is translation invariant and the product, you find this formula where phi is the mean jump rate of a site. It doesn't matter which site it is with the translation invariance. And of course, for this to define a probability measure, if you sum all of these, you must get something finite to normalize. And so this series, which is called as a partition function, must converge at phi for this to define a probability measure. The convergence of the radius of convergence of this series is exactly this limit, which we assumed for the jump rate to be strictly positive. And this is what ensures us that we have a non-trivial equilibrium state. And their formula is given by this for each marginal. So finally, you find that the equilibrium states are the product measures, where for each marginal they have this projection. And the whole family is exactly the family of these measures for all the values of phi, where zeta is finite. And this is the ground canonical ensemble. Then we want to reparameterize these by the density, and this can be done because the density function is strictly increasing, and so it has an inverse, okay, in its image. And then you set the measures parameterized by the density to be the measures parameterized by parameter phi, corresponding to the inverse of density function. And the critical density of the system is the supremum of all the admissible densities that you can get. And the problem is that above these densities, you do not have equilibrium states that correspond to these densities, and that's a big problem. Here are some examples of some cases. Whenever this is called the fugacity, the critical fugacity, when it is infinite, the critical density is always infinite. In the cases where it is finite, you can have both cases. The critical density can be infinite if the partition function diverges at the right endpoint, while in the corners, you have a finite density whenever it does not diverge at the right endpoint, at the critical fugacity. And in these cases, you have the equilibrium state that corresponds to the critical density. And these are the cases depending on the behavior of the partition function at the endpoint. You have the open interval doesn't contain the plus infinity when these two cases. In these cases, you have that. And you have a finite interval whenever the derivative of the partition function is finite at the right endpoint. In the particular case of the Evans model, you have this value for the critical density depending on the parameter B, and the canonical ensemble now is this family. And, okay, it's also worth conceptually noting that the inverse of the density function is the mean jump rate by this simple computation. Helps conceptually to have an idea of what this is. And now we'll say a bit about the correspondence between the canonical ensemble and the ground canonical ensemble. Because the transition probability was assumed to be reducible, it is easy to see that the communication classes of the zero-range process are all the hyperplanes that have a constant number of particles. By this, I mean the sum of all the particles at all sides. And by standard theory of Markov processes, there exists always a unique equilibrium state concentrated on these hyperplanes. which is the restriction of any of the measures of the grand canonical ensemble on this set, can be given by this way. And the phase transition phenomenon was first observed in the equivalence of ensembles, and by Evans it was proved rigorously by Groskinski, Schultz, and Spohn in Groskinski's PhD thesis. And it is stated like that. It says the relation between the canonical ensemble and the grand canonical ensemble as the ratio of particles approach particular density. And we see here that whenever the ratio of particles approaches a density, if the density is lower than the critical density, we have the convergence of the canonical ensemble to the grand canonical ensemble, while if the density that the canonical measure is approaching is greater than the critical density, we have a loss of density of the excess density. It is not observed. And this result will be used later. Okay, this of course implies weak convergence by Pinsker's inequality that bounds the total variation by the entropy. And this weak convergence shows us how one should extend the mean jump rate for values above the critical density, because I'm considering now bounded jump rates as in the Evans model. So by weak convergence, this will converge to this, which is exactly the function phi, which is considered constant for all the values after rho c. So I will not write a lot, but you have they are soaked. So you have the sorry. So we have somewhere here the critical density. The function phi is usually defined only up to the critical density. And according to this formula, you extend it as constant after that, when you have a finite critical density. And I always will consider this extension of phi above the critical density. This was already observed in Stefan's thesis. This is the right way to extend the Gaussian function. And this extension will play a role also in the one-block estimate a bit later. And Stefan also, in his thesis, along with other people around the years 2000, 2006, proved more explicitly this thing that the excess mass concentrates at the maximum site, and the secondly maximum occupied site has a number of particles that vanishes when rescaled, while here the maximally occupied site has a macroscopic portion of the particles. And so it's the maximum is of the order the excess mass times the number of sites, while the secondly occupied site is a log n, which vanishes with n. Anyway, now hydrodynamic limits. Hydrodynamic limits are expressed via the principle of local equilibrium. You have a correspondence between microscopic and macroscopic points. For instance, for each point in the microscopic torus, by the scaling space, we get a point in the macroscopic torus, and conversely, for each point in the macroscopic torus, we get a point in the microscopic torus. And one says that a state is a local equilibrium of some profile that takes values in admissible densities. If around each macroscopic point, it looks like the equilibrium state of density equal to the value of the profile at this point. And when one wants to prove the hydrodynamic limit, he wants to prove that if one starts from a local equilibrium of some profile, then the profile will evolve, the states will evolve, and during the revolution, they will remain local equilibriums along to a profile that varies with time now, and this will be the evolution of the density in a sense. And this is what one tries to prove in the hydrodynamic limits. An example of a local equilibrium state is this product measure. By taking any continuous profile, you define a product measure of this form, and this is a local equilibrium of profile rho. And Of course, since we are considering mean zero transition probabilities, the right scaling is diffusive scale. And there are mainly two methods of proving hydrodynamic limits. That's what I knew when I started my PhD, but later I found that Max Fati has found a method that is somewhere in between the relative entropy method and the Gopa-Nicolau entropy method, but I haven't studied it, his work, so I can't say for sure that I can't speak about it. But anyway, in the entropy method of the Gopa-Nicolau Varadan, one first wants to prove a relative compactness of the empirical density process, where you assign to each side, define a measure by assigning to each side of the points in the torus that correspond to the microscopic torus, the number of particles there. And first you want to prove that this is relatively compact. And then one has to do the replacement lemma, who in a sense allows us to close the equation. But in our case, this I haven't managed to do, and I don't think it's possible also, I don't know. Okay, and one requires uniqueness of solutions, because then he proves that this sequence has limit points, and then by proving that, by being able to close the equation and prove that, and use the uniqueness of solutions of the hydrodynamic equation, proves uniqueness of the limit, and so you have a limit actually in the end, and the limiting trajectory is the hydrodynamic limit. The other method is H.T.Yau's relative entropy method. This, in contrast, requires smoothness of the solutions, not uniqueness, and requires only the one block estimate, not the full replacement lemma, which is an advantage. And it requires estimates of the relative entropy with respect to the expected solutions for the hydrodynamic equation, in contrast to the entropy method, where you compare the evolution of the states with equilibrium states, not local equilibrium states. And by using these estimates, one can prove then Gronwall inequality for the entropy, which shows in essence that this is zero. And oops, sorry. And so in the limit, you get that this converges to the local equilibrium states of the according profile. And the result that I managed to prove for via the relative entropy method is to generalize the hydrodynamic limit in cases where you have finite density. But the thing is that I did that for profile is that start taking values, subcritical profiles that are continuous, say, and take values in the open interval below the critical density. And the hydrodynamic equation is this parabolic equation. And so if we take rho to be the solution of this equation, then the entropy is of little order of little o n, and that gives the convergence of these measures to these. This is actually, it's a simple computation. It's in Nadim's book that one can get the conservation of local equilibrium at all times. Here is all times. And the proof of this result was was made possible by extending the one block estimate to the cases where you have finite critical density. The proof exists in Kiblis-Nadim book under the assumption that the partition function diverges at the critical fugacity. And what I managed to do was to remove this assumption. With this assumption, for instance, this result was true only for beta between 0 and 1 in the Evans model. And by removing this assumption, it holds for all parameters. Here's a picture about how the functions phi look for various beta. These near the 0, they are not correct because the derivative is always strictly between 0 and infinity. Here it doesn't look very good. And the ingredient is first you need smooth solutions, as we said. Okay, by classic results on uniformly parabolic quasi-linear equations, when your function phi, your nonlinearity satisfies bounds from below and above, you have existence and regularity and the comparison principle, strong comparison principle. These are, for instance, in Vasquez's book, these results on the porous medium equation. And, but in our case, this does not hold because, as we saw in the pictures of phi, the phi is either constant after a value or either asymptotically constant. But one can circumvent easily this difficulty because we start from a subcritical profile, and then we can restrict the function phi to a smaller interval, and then extend it polynomially, degree of with as much regularity as we want, which is the degree of the polynomial that we have to use is equal to the regularity that we want to achieve. And by the comparison principle, then the solutions will always remain below this critical, a bit less than the critical density that we went, and so there will be solutions to the new PDE. And so we have actually, for subcritical profiles, smooth solutions. And we have the first ingredient needed by the relative entropy method. And in the particular case where beta is greater than 3, even the derivative at the critical densities satisfies bounds like these. So if we take beta to be greater than 5, where we have, say, where the second and the third derivative exist as real numbers, we can extend phi to a C3 function. And for beta greater than 5 in the end, one can allow at this stage the initial profile to even achieve the critical density. But that will pose a difficulty at a later stage. Anyway, the second ingredient that's needed is one block estimate, which allows the replacement of this process by this process, which is actually the jump rate over, which exchanges actually the jump rate at the site by the mean jump rate over a large box, where this is actually the mean density over a large box. L goes to infinity. And the precise result of the one block estimate is this. You start with a sequence of initial distributions that satisfies the big O entropy assumption. It has bounded entropy in a sense when rescaled by the number of sites. And it allows the replacement of this process we said by this, in this sense that with respect to the duality to all functions in L1 to continuous functions, this limit goes to 0. So whenever you have a function which is in this space, you can exchange this with this without having any error in the limit. And here actually phi is again the extended, where it is extended to be constant above rho c. And the whole proof relies on the equivalence of ensembles proved by Stefan Groskinski. In the original proof, it was used that the equivalence of ensembles holds for subcritical densities uniformly. But when I looked at the proof, I saw that the uniform convergence is not actually required. And I managed to do it without the uniform convergence by using only the equivalence of ensembles proved by Stefan Groskinski. And then once one has the one block estimate, can start, he has a smoothness solutions, can start to try to apply the relative entropy method to prove the hydrodynamic limit. As always, in the relative entropy method, it depends on this estimate on the entropy production, which is standard. This is also, again, in Lantim's book, but this is the starting point, in a sense, of the relative entropy method, and then one makes explicit computations in these all these terms. And in the end, he finds by using the one block estimate that you integrate here, then you have this limit, you integrate, you do computations, and you conclude that where m is the function given by this formula. In order to, we have to use one block estimate to arrive here. And there is also one small term here that will vanish when you take the limits of n and L going to infinity. After having this, okay, I will set by G this function, so I will be able to write this more compactly. And the previous bound is written this way. And then one applies the relative entropy inequality, the standard inequality. And this yields, after dividing by the number of sites, then taking the limits, yields exactly the Grolin-Wall inequality that we want, plus another term that we want to show that vanishes. This is how the relative entropy method works. And there's the proof deal is showing that this is actually 0, less than 0. And in the case that we allowed the initial profile to achieve the critical density, one would also, in order to show that this term vanishes, one would require the solutions of the PDE to satisfy a condition like this, where μt is the maximum of the solution. And I have no idea whether that holds or not. So I cannot say that I can allow the initial state to achieve the critical density. I don't know. This has to do with how quickly, because the maximum principle says that the solution, when you start from row C, it will start to fall and rise, and it has to do with the speed at which the comparison principle holds, actually. Anyway, and after doing that for subcritical densities, we're thinking, okay, what can we say about when starting from supercritical densities? And we decided that the right way to, after some thought, we concluded that the right way to consider supercritical initial conditions is to consider, so say we have here a space, here is a critical density. We decide to work with initial conditions that are measures that have an absolutely continuous part which is always below the critical density, and they have a Dirac mass just where the density, the absolutely continuous part of the density achieves the critical density. So we'll have a profile like that, and then a Dirac mass of some mass, but at the point where, only at the points where the density achieves, the absolutely continuous part achieves the critical density. And this was because if one tries to consider profiles that are above the critical density, then the equation does not see this part. I mean, one can do whatever he wants there, and the equation will not change because the function is phi and the derivative is 0, and this will not move. And even if you take one continuous profile like that, even that will remain a solution. And we decided to. But then we found some counterexamples in the 2 blocks estimate, and we decided to do something easier. This was when we tried to do what we can do with the entropy method of Guop and Nicolau-Varadan. And in this case, we start from initial state that is associated to some macroscopic profile in the sense that the empirical density in the limit, in the probability looks like this measure. The empirical density integrates in the limit functions just like this measure. And we want to see if we can prove some convergence for the trajectories for the laws of these the process. Okay, the empirical density was given by this formula. You can consider it the image of the process through this function. So we actually are studying now this process. And because the 2 blocks estimate does not hold in our case, I don't know whether the replacement lemma holds. I know the 2 blocks estimate does not hold, but that doesn't mean that the replacement lemma does not hold. We decided to do something easier, and we tried to find the hydrodynamic description via not by closing the equation, but using a non-closed form, something like the continuity equation. And for this, we looked at 2 non-conserved quantities, which is the empirical jump rate and the empirical current, which is given by this formula. And we try to prove now relative compactness of these quantities. And because at the microscopic level, the continuity equation holds in the sense that in the microscopic level, one has approximately something like, so this is the current, and and this is empirical. These are approximate relations. And so if we had a limit for these processes, by the portmanteau theorem, we'll be able to say at least that the continuity equation holds at the microscopic limit. And at first we tried to prove relative compactness of these quantities in the Skorohod space, but we couldn't. So the one process we were working is now the push forward of the zero-range process by the empirical jump rate function, the same by the empirical current. And we couldn't obtain the compactness in the relative compactness in the Skorohod topology. The reason maybe is because they are not conserved quantities, and I don't know. And we decided to look the same problem at some weaker topology. And so we chose some L-infinity spaces equipped with their W star topology. So for the empirical diffusion rate process, we chose this state space, the dual of L1, for L1 curves that take values in the space of continuous functions. And for the empirical current, we chose this space, which is the dual of all curves taking values in C1 vector valued functions. And in these spaces, it is easy to obtain relative compactness because one has Lauglo type theorems that bounded sets are relatively compact. And for instance, I'll go a bit back to show the formula of the current. Here we have, we are not rescaling by 1 over d, but we have 1 over d minus 1. But when you try to evaluate this at some function, you can do an integration by parts, and you can pass this ej to the function g, and then you have a function g evaluated, the difference of a function g evaluated at 2 points that differ 1 over n, and because you are in C1, the functions are Lipschitz also, and so you can take this factor and you can do this 1 over d, and you can prove boundedness. And so you get easily the relative compactness in these spaces. And so then one sets this product space as because we want to consider the triples, where you have the empirical density, empirical jump rate, and empirical current. Each one takes values in the respective spaces, and we push forward the zero-range process in this space. And in this space, we can get easily relative compactness, and then by the portmanteau theorem and this microscopic relation, one gets the validity of the continuity equation for all the limiting laws of this. The result is as follows. We start with starting a zero-range process with bound and jump rate. We start with an initial state that has a third moments. That is in order to consider martingales and not local martingales. It's not so important. Anyway, and you start with this sequence being associated to a macroscopic profile. What is proved is that this sequence is sequentially relatively compact in the weak topology of the space. And any limit point of this sequence is concentrated on trajectories such that, first, they are weakly continuous. This follows by the validity of the continuity equation. And they start from the measure that our sequence of initial states was associated. The limiting curves of the empirical jump rate are absolutely continuous, and they are all bounded above by the critical fugacity. This follows by the one block estimate. Because in the limit we get the trajectories of the empirical current to be order 1 distributions, because we took them in a space where they were in the dual of C1. We have to prove additionally that they are indeed measures, and this is also proved by energy estimate we'll show you afterwards. So the current is in fact actually a measure, which is absolutely continuous with respect to the Beck measure, and the continuity equation holds in the sense of distributions. This is the most difficult part actually, but it follows. Okay, I think I will skip some details of the proof. Okay, and this is the most difficult part. Follows by this energy estimate. This is also something very close like that is in Landim's book, but there he uses the replacement lemma. And, when one has proven the relative compactness of the empirical jump rate, one sees that he doesn't need the replacement lemma, and he can just state the same things for the empirical jump rates, which shows actually that the empirical jump rate is in almost surely in H1, and because the current is a gradient by this relation without the ends. The current is a gradient of this, which is in H1, so this is in L1, so it's actually in L1, and the current is absolutely continuous with respect to the Lebesgue measure. And this is the result in the continuity equation. And I would like to finish with a conjecture about what I didn't manage to prove. As I said before, in order to describe the condensation phenomenon, would like to allow measure-valued solutions, and that's why we tend to the continuity equation, because it makes it very easy to consider measure-valued solutions. And for now, for the rest, I will concentrate in the case of the Evans model for beta between 0 and 2. In this case, the critical density is infinite, but still, again, that doesn't mean that it's not condensing, it's weakly condensing. For instance, if you started the corresponding PDE with a Dirac mass somewhere, this Dirac mass will not dissolve immediately. And one has to say how he can make sense of this equation when mu is a measure. And that's a bit difficult in general, but this can be interpreted as a gradient flow in the Wasserstein space of probability measures, at least in dimension d equals 1. And my conjecture is that exactly this gradient flow is the hydrodynamic equation, and I will try to argue a bit about that now. I don't know if it will be convincing. First of all, it will be the gradient flow with respect to the following energy functional. Here it doesn't have superlinear growth, so we have to include also this term for the singular part, where this is the Radon-Nikodym decomposition with respect to the Lebesgue measure on the torus. And the energy is chosen the ordinary way by this equation. So it's given by this formula. And this is the superlinear, the growth at infinity of the energy. Okay. We consider the one-dimensional case. Why? Because in the condensed case, we have this limit, which shows that for dimensions greater or equal than 2, the McCann conditions are not satisfied. So this functional, the energy functional, is not lambda displacement convex, at least for lambda greater or equal than 0, which will give you uniqueness of solutions. But by results of Villani in his book, Optimal Transport, Old and New, I think they're in chapter 17, it shows that in dimension D, this function H epsilon is actually displacement convex. And by work of Shinichi Ota on Wasserstein gradient flows on space, over compact Alexandrov spaces, he shows that displacement convex functions give well-defined gradient flows. So given an initial distribution, we have a gradient curve, which will satisfy this, because we have lambda convexity with lambda equals 0. And so actually, this shows that the gradient, the gradient flow that I'm saying will be the hydrodynamic limit actually exists in a sense. It has uniqueness and all that we will require. And these conditions that is in Ambrosio's book that will tell that when you start from a profile that has a Dirac mass somewhere will dissolve at any small positive time does not hold. So actually, there is a possibility that the condensate will persist. I don't know if this is necessary and sufficient, but it is surely sufficient for the condensates to dissolve at any positive time, but that doesn't hold. I don't know if it is necessary. Okay, and then there is a work of Savare, Fornaro, Licini, and Toscani in 2010, where they gave a characterization of the gradient flow of this functional h epsilon. In the case of the real line and in the presence of C2 potential, but their characterization is closer to the spirit of, in the sense of distributions, which is closer to the continuity equation in the sense of distribution that we have shown and all that. And here they studied the same problem, but they had also this drift term here, and so they have the energy, the corresponding energy, which is like that. And they are considering solutions that are in a class like this, which are measures like this I described. They consider measures that have absolutely continuous part that has a continuous representative. And the singular part is concentrated exactly where the measure achieves the critical density. This is intuitively very good because in order to have a phase transition somewhere in your space and have a change of phase, the medium has to have, intuitively has to reach the critical density first. It's like, I know that temperature has nothing to do with the model, but it's like when you want to freeze something, if you have water and you want to freeze, first you have to get temperature to 0. It cannot freeze when temperature is not the critical temperature. And something, expect something like that to hold also with densities. And they also define this functional. In our case, we don't have any drift, so this will not be there. This will not be there. And they define it by this formula. And then they prove that the gradient flows are characterized by these conditions. They prove that a curve inside this space of these, they say them measures with continuous density, is a gradient flow of the functional we discussed. If the measure is always in this space, if the integral of the function as j is finite, and if this equation holds in the sense of distributions, this estimate is very close to the energy estimate that gave us that the empirical current is indeed a measure. And so in order for one to prove that this gradient flow is actually the hydrodynamic limit, one needs to show these two things, that the density will always remain in this space, and that the limiting empirical jump rate is the mean jump rate of the absolutely continuous part of the density, which this is the difficult part, actually. And this is, in essence, the replacement lemma. But now at least we have an idea on what to expect of the replacement lemma. And in dimension D, the fact that this has a continuous density is easy, because since this is in H1, in dimension 1, it will be also continuous, so this will be continuous. And so if one proves that, in order to prove that this is actually, that this gradient flow is the hydrodynamic limit, one will have to prove that at all times the condensate will exist only where the density is critical. And this. And I haven't managed to prove any of these, so I think I will stop here. And thank you for your attention. No, without a drift, you expect that it will not move. So the thing is to find out if it exchanges particles with the bulk and what happens. Because in order for the condensate to move, it first has to dissolve and then emerge somewhere else, which takes time larger than the diffusive time scale. I mean, it's time n to the 1 plus b to observe this metastable behavior to have it dissolve. So it will, when it moves, according to the results of Savara and Licini, when it moves, it follows the drift, the condensate. That's why they were looking at drift equations. If you don't have any drift, we expect it to stay where it is when you start, but it will just exchange mass with the bulk. So it's like having a PDE where you have a hole somewhere where you can lose and gain mass, like you have a boundary where you can lose and take particles. Yes, yes, there are, and the scales at which that happens, and I think they are in the Evans model. They are of the scale 1 n to the 1 plus b, something like that, which for b greater than 1 are greater than the